Definition of the transpose of a matrix. Hello everyone. Today, we are going to begin our lesson on a key concept in linear algebra. To start off, it is important to understand that the transpose is one of the most fundamental operations we can perform on a matrix. Now, what does this actually mean in practical terms? Simply put, transposing a matrix involves flipping it over its main diagonal. By doing this, we are effectively switching the rows and the columns. In the upcoming slides, we will explore the conceptual side of this operation, look at the formal mathematical definition, and work through some step-by-step examples to ensure you have a complete grasp of the process. Conceptual understanding. To start, I want you to imagine a matrix not just as a collection of numbers, but as a structured table of data. For example, if you have a table where the rows represent different items and the columns represent different attributes of those items, transposing that table would simply mean swapping those roles. In the transposed version, the attributes would now be represented by the rows, and the items would be represented by the columns. This leads us to the core rule of this operation, which is essential to remember. First, the first row of the original matrix is rewritten to become the first column of the transposed matrix. Following the same logic, the second row of the original matrix becomes the second column of the transposed matrix. You simply continue this process for all remaining rows in the matrix until the transformation is complete. Now that we have introduced the basic concept of flipping a matrix over its main diagonal, let us build a more intuitive conceptual understanding. Once you are comfortable with this visual process, we will move on to the formal mathematical definition and the notation used to describe this operation. Formal mathematical definition. Now that we have a conceptual understanding of flipping a matrix, let us look at the formal mathematical definition. First, let us define our starting point. Suppose we have a matrix, which we will call capital A, with an order of m by n in this context. M represents the total number of rows, and n represents the total number of columns. When we perform the transpose operation on this matrix, we need a way to denote it. You will typically see the transpose of matrix capital A written as either a prime or a transpose. Both symbols mean the exact same thing. To understand exactly how the elements move, let us look at the indexing. If we take an element located in the ith row and jth column of matrix capital A, which we denote as a sub-ij, that same element will move to the jth row and ith column in the transposed matrix, capital A transpose. Essentially, the row and column indices are swapped. To express this mathematically, if matrix capital A is defined as the collection of elements a sub-ij with a dimension of m by n, then its transpose, capital A transpose, is defined as the collection of elements a sub j, I with a dimension of n by m. As you can see from this notation, the roles of m and n have switched. We will discuss the implications of this change in dimensions in the very next slide. Observation on dimensions. Now, let's take a moment to look at a very important consequence of the process we just discussed. You will notice that when we transpose a matrix, the overall order or the dimensions of the matrix changes. To put this in formal terms, if our original matrix, which we have called matrix A, is of order m by n, meaning it has m rows and n columns, then its transpose, denoted as a transpose, will always be of order n by m essentially. The number of rows in the original matrix becomes the number of columns in the transposed matrix, and the number of columns becomes the number of rows. Keeping this dimension shift in mind is crucial, as we will see how this looks in a practical scenario in the next slide through a real-world analogy. Real-world analogy. Imagine you are looking at a school grade sheet. In this scenario, let's say the rows represent the students, specifically student A, student B, and student C, while the columns represent the subjects, such as mathematics, physics, and chemistry. If you were to transpose this data, the entire structure of the table would flip. The subjects, which were originally the columns, would now become the rows, and the students, who were originally the rows, would now become the columns. The most important thing to realize here is that the actual marks, the data points themselves, remain exactly the same. No numbers are changed. We have simply rotated the perspective of the data. Now that we have covered the formal mathematical definition and the notation, let us look at a real-world analogy to help you visualize how this operation works in practice. This conceptual shift is exactly what happens when we move from a matrix of one dimension to its transpose. Now that we have this mental image, let us apply it to a concrete numerical example in the next slide. Step-by-step example. Now that we have covered the theoretical definition and the real-world analogy, let us apply these concepts to a practical example to see exactly how the process works. Let us consider a matrix, which we will call matrix A. This is a 3x2 matrix, meaning it consists of 3 rows and 2 columns. The elements are arranged as follows. The first row contains 2 and 5, the second row contains 4 and 8, and the third row contains 1 and 0. To find the transpose of this matrix, which we denote as a transpose, we will follow a systematic step-by-step approach. Step 1. We identify the first row of matrix A. The first row consists of the elements 2 and 5. According to the rule we discussed in the previous slides, this row will now become the first column of our transposed matrix. Therefore, we write 2 in the first row and 5 directly beneath it in the second row of the first column. Step 2. Next, we identify the second row. The second row contains the elements 4 and 8. We now move these into the second column of a transpose. This means 4 will be placed in the first row, second column, and 8 will be placed in the second row, second column. Step 3. Finally, we identify the third row, which contains the elements 1 and 0. Following the same logic, this row becomes the third column of our transposed matrix. We place 1 in the first row, third column, and 0 in the second row, third column. As you can see, by systematically converting each row into a column, we have successfully constructed the transpose of matrix A. In the next slide, we will observe how this operation has affected the overall dimensions of the matrix. Final result. Now that we have completed the step-by-step process, let's observe the final result. As you can see, the original matrix A had an order of 3x2. However, after performing the transpose operation, the resulting matrix, a transpose, now has an order of 2x3. This perfectly illustrates the principle we discussed in the earlier slides. The dimensions have been swapped, confirming that the number of rows in the original matrix has become the number of columns in the transposed matrix. Key takeaways. First, regarding the operation. Remember that transposing is simply the process of interchanging the rows and the columns of a matrix. In terms of notation, you will see the transpose of matrix A denoted as a transpose, written with a capital T superscript, or alternatively as a prime. Next, let's recap the dimension shift we observed in our previous example. If the original matrix is of order m by n, its transpose will always result in a matrix of order n by m. Finally, looking at the element mapping, the element located at the ith row and jth column of the original matrix moves to the jth row and ith column in the transposed matrix. Now that we have walked through the conceptual definitions and a practical example, let us summarize the key takeaways to ensure you have a solid grasp of the topic. Keep these 4 fundamental points in mind, as they will be crucial in helping you avoid some of the common mistakes we will discuss in the final slide. Common mistakes to avoid. Now that we have covered the definition and walked through a practical example, let us conclude by discussing some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, let's talk about confusing the order of the matrix. A frequent error students make is forgetting to flip the dimensions. As we saw in our previous example, the dimensions must swap. Always remember, if your original matrix is of order 3x2, its transpose must be of order 2x3. Secondly, be careful with incorrect mapping. Some students mistakenly believe that transposing simply means reversing the order of the elements within the existing rows. This is incorrect. Remember the core rule we discussed earlier. The entire row must move to become a column. You are not just rearranging elements within a row, you are changing the orientation of the data entirely. Finally, let's address notation confusion. Depending on your textbook or your instructor, the transpose may be denoted as a transpose or a prime. It is crucial that you use the specific symbol required in your course. This prevents any confusion with other matrix operations, such as matrix inversion, which is a completely different process that we will encounter later in our studies.